Good morning, everybody, and thanks for coming. I was asked to give an overview of the on-farm precision experimentation and the data-intensive farm management network. So that's what I'm going to do. Some of you have heard this several times before. Just concentrate on your coffee, I guess. So, all right, let's go. So maybe some of you have participated in small plot field trials. And that takes work. You lay out small plots with measuring tape and orange flags. And then it takes a lot of work by hand, either with small machines or manual labor. Often there's student labor, technician labor. Brittany knows they make so much money that this can be really expensive. And so the question is, why do people run field trials? And what can they do for precision ag management? So I'm going to give you just a little bit of economic theory here, and then more later. I'll try not to go overboard on your hair. But if you take Ag Econ 101, in the first month, you're going to see this diagram, okay? And that first thing there is generally called a production function or a yield response function, which just says, okay, you got an input like here, nitrogen on the horizontal axis, and yield responds to nitrogen, okay? And probably more nitrogen, more yield. Okay. And what you find out is that if you know the price of the input and divide that by the price of the output, the profit maximizing N is the one that is where the slope equals that price ratio. I won't go into too many details, but that's just something you can show, in a 45-minute lecture to undergraduate students, okay? And then there's also a profit maximizing amount of production, which of course is not maximum yield, and we can discuss that too. All right. Small plot trials generate input rate and yield data used to estimate yield response curves. So here is an aerial photo of an actual small plot trial. And you can see here that they're using seven different nitrogen rates from 0 to 24. And then there's 3 rows of 7, and they've got them kind of randomized here. So some places they're putting 8 gallons on, and some places they're putting 0 gallons on. And then they come in and they'll harvest these by hand. And then that gives them data. Like maybe this from 0 got that much yield on their plot. Maybe here 24, they got that much yield. And then you put all those dots together, and you can get an estimate of what the yield response looks like. Okay. Crop scientists have been trying to figure this out for hundreds and hundreds of years. I found this one from 17. It was published in 1784, but the work was done in like 1767. Okay. So people have known for a very, very, very long time that this is what they need to know if they want to know how to put inputs on, efficiently and profitably. They got to know how yield responds to that input. So that's very basic. This is actually where statistics started. Modern statistics. This is a research station in England, and this guy named E. Fisher, really smart guy, got a job working with this data, and he said, well, geez, this is kind of complicated. He figured out all this mathematical stuff that led to modern statistics. So one thing that's I really enjoy about this research is, one, it's just at the very fundamentals of agricultural economics and the very fundamental stage of statistics. This is sort of the question that started the whole thing, and it's fun to work on that question. Bob Dunker over here, he used to manage the moral plots. This is the University of Illinois. These started in 1876. This is across the street from my office. All right. More generally, of course, life is more complicated. It's not like yield just responds to nitrogen. Yield responds to other managed inputs, herbicides, seed variety, etc. Spatially dependent characteristics like soil, calcium content, siltiness of the soil, topographical slope, and then weather. Okay. And so I'm calling this the God function, this F. It says that X is N rate, tillage practice, C is slope, soil content, rain second week of July. That's what you would want to know if you could. Okay. If you knew what that was like, you'd sort of be all set. Except, of course, you can't control weather, so then you'd have to deal with various things, okay? So that's what everybody's been wanting to know for a very long time. And to keep that fundamental concept in mind will help you defend yourself against some precision agriculture advertisements that say, if I take pictures of satellites if I take enough pictures from satellites, I can tell you how to farm. Okay, and I'll explain why that's not going to be enough to know how to farm. You have to have a different kind of data than just pictures from the sky. Here we go. The key challenge in precision agriculture is that we don't know that picture. Okay, what I've got here is, here's area A, and it's got like soil type A, soil type B. The weather is like 2022. And in different areas, you get different yield response functions, different yield response curves, and therefore you need to manage those differently. And the problem is, we don't know those curves. And if you don't know those curves, I mean, you just, what do you know, right? Obviously, we know something about these curves. Farmers intuitively know something about these curves, but knowing more would be better. All right. I don't think anybody knows very much about the God function. And that is something that wasn't appreciated in the 1990s when precision agricultural technology first hit the commercial markets. They really thought they could look at a yield map, multiply it by 1.2, and tell how many farmers, how much nitrogen to put down. And they found out pretty quick that was wrong. And farmers started saying, oh, that's a beautiful yield map. Now what do I do with it? Okay. All right. Why not? I don't think we know very much about the God function because there's a lack of data. And how could this be? We just said that agronomists have been doing small plot experiments forever to figure out response functions. So how could this possibly be? The problem with small plot trials is that they're small, okay? And they're labor intensive, and so they're expensive. Moreover, the data they provide aren't from the field you're trying to manage. Great, someplace in Iowa, they did a small plot trial. Maybe in 10 places in Iowa, in different counties, they did a small plot trial. Well, I'm in Nebraska, or I'm in Ukraine. What do those trials, or I'm across the street. What happened on those small, I mean, a small plot trial is maybe twice as big as this room a lot of times. What does that particular trial in that particular place on that particular piece of ground mean for other places? And it might not mean a whole lot because places are different. All right. So all this talk about agricultural big data might be about a gazillion petabytes of data from satellites or sensors, but that data is not going to be very useful for improving input management unless it is accompanied by data that looks to see what happens when input management is changed. In other words, if you take pictures from the sky, but the input management is the same everywhere, basically the farmer put 200 pounds of nitrogen on this field, then you're not going to know how to manage better because there's no data on it. Okay, fundamentally, if you want to see how to do something, you have to change what you do and see the effects. So, no matter how many drones we fly, if our data doesn't feature sufficiently varied input rates, it's usually not possible to determine optimal input rates from data. In other words, if this is what your data looks like, very little variance in the input, okay, you're not going to be able to fit a curve through a column of data. Okay, and that's the whole problem with just taking pictures from the sky and giving farmers prescriptions about what they should do next, okay, with their inputs. Okay, you can't identify these curves, what they look like, if you don't vary very much. And that's the whole reason people have been doing these trials, all these. Okay. And so what you do is if you vary in a lot, then you got a chance. I hope that's not mine. That's all right. You've got a chance to figure out what those curves look like. Now, that doesn't mean it's easy, but you got a chance. Okay. Despite all this research, until fairly recently, it's a stretch to say that university-led and fertilizer management recommendations were based on data or statistical analysis. And that's a little bit to the shame of agricultural universities. I think it was pretty hard to go to farmers and say, you know, we don't really know very much about how much of the input you should put in the ground, even though, you know, you're giving us your tax money every year. We just can't figure that one out, sorry. And so I think people began to believe things that everybody began to believe, that you could manage an input this way out by this rule of thumb, et cetera, et cetera. And it got to the point where people just were believing what they believed because everybody believed it. And one great thing about precision agriculture is that it's broken down a lot of those beliefs, because people have seen with their own eyes that's not working. All right. All right. In the past, university fertilizer management recommendations could only be rules of thumb. For example, for corn, until about 2007, there was this thing called the 1.2 rule. Okay, and it worked like this. Farmer would ask the crop consultant or the extension agent, what's my profit maximizing end rate? And she'd say, well, what yield do you want? And my brother is an agronomist. And so when he first told me this is the way they put nitrogen on corn, I thought, well, I want the yield that makes me the most money. That's the yield I want. And he'd say, oh, my goal is to put 200 bushels per acre out, get 200 bushels per acre. And she'd say, well, just multiply that by 1.2. 1.2 times 200 is 240 pounds of N per acre. There you go. And that's how they managed corn since the 60s. Okay. It came from some studies that were just nonsense. I mean, the guy's dead. I don't speak ill of the dead. But this guy named George Sanford took a lot of bad data, put it together, waved his hands, and created something that affected how everybody fertilized everything all over the world for the next 60 years, 50 years. All right. It was not based on good data. This is from his paper. The reality is there have been a lot of studies over the past 20 years that keep showing that the optimal nitrogen rate is not related to yield. Okay. You can have really good parts of the field where you don't need much nitrogen and really poor parts of the field where you need a lot of nitrogen to be economic, to maximize profits. All right. So what about these dozens of input application decision tool software packages on the market? And so, you see these you go to a farm data extravaganza or read any agricultural website, and you're always getting them say, buy our software and we'll help you make $30 more per acre, et cetera, et cetera, et cetera. I think much of those claims, I know that they're not made by getting data from the place where you're trying to manage. They're not made by getting data from the field the farmer's trying to manage. And that's a problem. Okay, here's Encirca saying they can increase your return on investment by 74%. Adapt In is saying they can make you $30 more per acre if you use their software. So we do know some things, of course. There's a lot of new technologies that are making it much easier to measure these field characteristics, which I'm calling C, right? Here you see somebody making an electroconductivity map with a Veris machine. Here's somebody's taking pictures from a drone. Those are all measurements of characteristics, and I would say that those are good. But if you don't complement those with data, with input rate, yield data from trials, I don't think you're getting yourself anywhere. All right. Here's an alternative, and that's what this conference is about. The alternative is on-farm precision experimentation. OFPEs are way bigger, way cheaper, and implemented by farmers on their own fields to get information about how to manage those same fields. Here's one. Okay, so this is one we designed for a farm in South Dakota. It put 3 fields together and it's over 1,000 acres. Okay, so instead of something the size of this room, you're dealing with something, about more than a mile by 2 miles. Okay, and each one of these little rectangles right there, they, like in a small plot trial, you put different nitrogen rates on there, or seed rates, or whatever you're dealing with. And then, some of them get high rates, 224, some of them get low rates, 112. And you can do that all over the field, and you get nice data with a nice variance like you want. And then you have a shot at thinking about what this curve looks like. And I think it's revolutionary. Okay, I think it's a revolutionary thing for agronomic science and for data collection in agronomics. Okay, and so the data-intensive farm management project has done about 300 of these trials over the past 6 years. We did a 100-acre cottonseed trial in Texas. What you're seeing there is actual as planted rates, and you can see them changing with the trial design. We did a 250 acre corn fertilizer and seed rate trial in Argentina. So this was a huge field, 500, it's like a 200 hectare field, and we used half of it. We did a soybean trial in South Africa. And so how this worked. Okay, the farmers sent us a boundary file for the field. A boundary file is just a kind of a big polygon with a bunch of, it's defined by a bunch of longitude and latitude points. Most farmers who deal with precision technology, they deal with these all the time. Okay. And then we use computer code to create shape files that partition the field into plots with different seed rates and assigned to the plots. So we can make, we call this a trial design. It's just a bunch of longitude and latitude points, and then it's got a number that says, tractor, when you get to this longitude and latitude point, have the applicator put down however much the trial design says to put down. And they can suck that into their, say, this is a seed rate trial, they can suck that into their planter computer, and then all they need to drive. Admit, Xiaofei. Is this me? How do I do this? How do you? Just keep on. Okay. So here, what you can see here in the yellow circle, this is one of our farmers. He took a video of this with his iPhone. Okay, and at this point in the field, he was supposed to be putting down. The field trial designs had put down 30,000 seed per acre. It was actually at this point putting down 29,650 seeds per acre. That was the estimate. Okay, and of course, because he's got his steering locked in with GIS, he can take a movie while he drives. And so as he does that, you'll see this thing bounce around 29.57. That goes up to 42, and pretty soon there's 38. That goes going to go up to 42 in a second, just as well. Okay. So literally, instead of taking out measuring tapes and a bunch of technicians or grad students and doing things on something the size of a basketball court, this guy can take a movie while he's putting the trial in the ground. Okay, so it's pretty easy. Okay, and that movie gets us data. This is as planted data. You can see here, what I can tell is that, and it's not perfect, here you can see that for some reason the planter planted higher than it wanted to, but the background color here is the targeted rate. So maybe this is 25,000 seed per acre. Maybe this is 40,000 seed per acre where it's darker. And these as planted points are saying how much was actually applied. And you can see that generally the as planted points are the same color as the background, not all the time. Sometimes it takes just a little bit of time for this. I can tell that this planter was going this way. It took just a few feet to adjust as it went from a higher rate zone to a lower rate zone. All right. At harvest, what you do is you run the combine up these plots, right? And so then you're getting yield from the same place that you put down the experiment. All right. One of our farmers put this on the internet, on YouTube, and he said I could show it to you. Is there no sound? There's no sound? Anyway, he ends this. He says this is Winty Farms, and this shows a harvester that my brother has been driving. He's going up a seed rate trial, and he says this isn't technology great. Okay, so he really enjoyed this. All right.
Was that the background? Sorry.
No, go ahead.
So you actually have the plot design as the background of the harvest map, so that he's going across the field, you can see the.
I think so. Yeah. Yeah. And yeah, that's the as planted data, and then that's the background. Now that you'll see that we're designing software that we want to do lots of great stuff, and he's really tech savvy guy, so he may have done a little bit of this himself. I'm not sure. Well, he's a really smart guy, but obviously this is what we want. What you do see is when you're in the planter, it will show you what rate. You can see what plot you're in and how much you're supposed to put down. This is a little special, but we're trying to design software that will do all these kinds of things. And we have many of you here because you work with this kind of things with farmers, your CCAs, and you know what you're looking for, and we want to hear what you're looking for. Okay. All right. Basically, you'll see we did a bunch of trials for this big South Dakota farm. These are different fields, and these are all as planted data after it's been processed. We'll talk about processing later, but basically, if you've ever dealt with yield data or as applied data, there's a lot of weird stuff in it that you have to throw out. And you can either spend 3 days pointing and clicking and taking stuff out, or you can come up with you can be Brittany Edge and come up with some computer algorithms that will do that for you. Okay, Brittany Edge and Tarmiel. All right. And so we have computer code that will clean these, and it will also yank out some places where the data wasn't any good for whatever reason. So this is as applied, as planted data on this farm. All right. And then we can use all this data to try to do, interesting things to help farmers make more money. Now, nothing's perfect. I'm not telling you this is easy. I think when Brittany's my age, I hope she's still trying to figure this one out. But I think we can learn a lot already from what we're doing. All right. I won't go into too much detail here, but this is one statistical method that might be used. I can't stop it, so I don't really quite know what to do. This is called geographically weighted regression. And what happens is, as this is going across the field, this is showing what the yield looked like in the neighborhood of that field. And so you can tell when they're getting high yield response, and when it goes like this, you're getting low yield response. And as a result, you can map out the places that have high yield response and the places that have low yield productivity. And this is just the kind of information you want to manage things site specifically. All right. And you can come up with what are called prescriptions. Okay, so if you're a farmer, you can buy a prescription either from somebody who makes it online that you can get to through myjohndeere.com or from a consultant. And we can also do that, but we're trying to base these prescriptions on what we see in the data. Now, it's much harder than this, of course, but that's the basic idea. And we can come up with different zones and find zones where things are not very productive, where yield response is flat, and places where yield response is steep. And so, of course, you want to put more seeds here and less seeds here. Okay. And on these fields, given the weather, which in South Dakota can vary a great deal, but we can say after 1 year's experiments, oh, this is what you should have done if you knew what the weather was going to be ahead of time. Now, that doesn't answer the big question is what should I do generally when I don't know what the weather is going to be ahead of time. That takes more information and more yields trials, but it is something we're trying to make, as Bruce says, farmers are gamblers, and we can try to make farmers better gamblers. Okay, so, okay, who are we? Who's working and participating in the DIFM project? Bunch of people. People in a bunch of states. These are professors and grad students. And then we've got some folks in Canada. Here in Quebec, I'm talking to a bunch of people up in Alberta. We're working in Brazil, Uruguay, Argentina, South Africa. We were going to run 17 trials in Ukraine last year. And of course, the war got in the way, and we're hoping that ends soon, of course. And they can continue with research. So this is a big project. We've gotten $8 million in USDA funding over the past 6 years. So they thought this was a good idea, and that's the situation. These are our 2021 North American trials. So you can see those are all over the place too. There's a lot in Illinois just because that's where we are. Some of us are, but we're doing this all over, and we're going to do next year, 2023, there will be even more. All right. Okay. We're also working with community colleges. We have applied for a government grant to create a class. I didn't realize this, I should have known, but community colleges around the US, there's like 50 of them that have precision agriculture programs that generally people can come in, take 2 years, and then they can use that to be, to help their family run their farm, or some of them want to become crop consultants and et cetera. So there's a whole industry out there of young people getting educated in precision technology. And so 5 of those schools are going to join DIFM, and we're going to create a class where if you have 2 or 3 people at Hawkeye Community College in Iowa who would like to learn about on-farm precision experimentation, they can take this class, which is taught by 5 different professors, and do it virtually. So normally you could never get your institution to say, yeah, this is good, let's create a class for 3 people because it's just too expensive. But of course, what the pandemic showed us is that you can you can actually have classes online, and that opens the possibilities for having something that would not be cost effective become cost effective. So this is our hope. Okay. Said that. We are working with the Oracle company, and Keith Curran will tell you more about this tomorrow. We don't want to do 100 trials per year. We have a vision where the world does these trials the way farmers soil sample. If you're a farmer, a lot of places, you probably in a field, you soil sample every 3 or 4 years. And in some parts of the field, soil sampling analysis is expensive. And every few years you get that information and you use it, and you talk with your advisor about it, and you try to make your management better with that. And farmers do that all the time. We aren't thinking that every farmer is going to run a trial on every field and every year, but we like to see a world where lots of farmers are running trials in parts of their farms all the time. Every year they're running some of those and finding. And so that would mean that we have to run tens of thousands of field trials per year, not 100. And of course, that means that we have to automate all sorts of things. And that's part of what we're doing. So we're not just putting trials in the ground. We're trying to create what I'm going to call a cyber infrastructure that allows the world to do many, many, many of these per year. Our current hope is to get the NRCS, the National Natural Resources Conservation Service, to create a kind of computer website where this becomes a thing that people can do. It's a public good, where consultants, et cetera, can use this. We want to make it open source, so if people want to write their own code to do various things, they'd be able to do that. So that's the vision, and we've talked to NRCS about it, and they seem open to the idea. So we just have to create some good stuff and see if that happens. So that's our vision. All right. Every farmer can't have someone with a PhD to analyze the farm's data to make reservations, and that's why we need to automate this. Okay. We're building a cyber infrastructure, and I'm not going to go into this very much because I'm going to give a talk on it later. But what that cyber infrastructure does is make it possible to run all these trials. Now, after you run the trials, of course, you have to get something with the data. You have to get the data, put it somewhere. You have to process the data. And in this, we've done a lot. We have wrote a computer code, and we're actually have figured out good ways to process this data so it doesn't take one person 3 days to do it. And then a bunch of people, the economists, computer scientists, crop modelers, agronomists, are trying to figure out, okay, once we get this data, how do we analyze it? So we're trying to create an analytical engine that will figure stuff out without somebody with a PhD having to spend 2 months looking at the data. Now, of course, what you can do automatically is not going to be the same as what an individual could do in 2 months. But we don't have to be perfect. We just have to be better. So we're trying to create an analytical engine that will make things, help us use this data efficiently. All right. Results. We think this can turn into better input management decisions, higher profits. When we do this, the farmers who participate with us, they own their own data. We don't own the data. We don't let anybody else use it without the farmer's written permission. And we certainly don't sell the data to anyone. And the farmers, we assure anonymity. All right. We're paying farmers $1,000 stipend. Basically, this gets our data back. We're having trouble getting farmers to send us their data. They get busy after harvest, and then pretty soon it's February. So we thought, well, we need to give them some money anyway, so we give them $1,000, basically. We call it a thank you gift, but it's also they get it after they send us the data. And then we have funding to give farmers full compensation for profit losses. Okay, so we have a pretty good way to estimate, oh, you lost $2,000 because you ran because we had some really low rates and some really high rates. And if you had just done your usual thing, you would have made $2,000 more. The NRCS very much wants us to write those farmers checks. They had this whole on-farm field trial program. And the point of the program was to subsidize farmers to run experiments. And so when I saw that that was a thing, we jumped on it. And so the NRCS is trying to get farmers to run these experiments, and they very much want to pay them to run them so they don't lose money. Yes.
Sorry, so is there a waiver that happens for their yield reporting?
Yeah, that's what you mean for the insurance and all that?
Yes, like if you lose 10 bushels or 20 bushels.
Right.
It actually penalizes the grower. For
Right.
cycles.
We don't have that, but that's something for us to consider. Frankly, these are some big farmers and they don't care. Frankly, they're not doing it for the money, they're in it for the information, which is where most of the value is. But you make a good point, and no, we don't have that. Absolutely. So that's something that we need to do better. Yeah. Okay. Now, we also have been allowed, if somebody's a crop consultant, right, we can pay them $3,000 if they work with us. Now, what we want crop consultants to do is to work with farmers to design these trials, run these trials, use our software, and then work with us and Hiking and some other people to tell us, okay, we're trying to make software that's user-friendly, and we can't do that unless we test drive it with real people. Okay, so $3,000 isn't a lot for a crop consultant, but at least it's a little bit and helps offset some of the value of their time. So we are looking for CCAs and co-ops, et cetera, to work with us on this. Okay, what are we finding? Some general findings. When we went into this, we thought a lot of people were saying a lot of corn farmers put on way more nitrogen than was economically optimal, which would have been good in the sense that you could then cut nitrogen, you get environmental benefits, and everybody make more profits, and you have a complete win-win situation. We're not seeing that. We're not. Some farmers, we're not seeing like egregious tons of nitrogen being put on and farmers losing money. So that's something I think that was really not known before this project, and I'm very confident in that finding. We are finding that on Illinois, flat and black Illinois fields, precision agriculture doesn't pay off very often. Okay, the fields don't have enough variation to justify the cost of variable rate technology. Now, our experiments and the data can help farmers farm better uniformly. They can say, oh, that soybean rate, that 80,000 seeds a bushel was too low or too high, and I've had farmers tell me that we made them a lot of money because they did a couple of years of soybean seed rate trials and they were just overseeding. They were just throwing money away on seed. And so what we're finding is not necessarily something that makes the precision ag industry happy, which is that some places it doesn't make sense. Now, if you're in Washington and you're Palouse, and what side of the hill you're on makes a huge difference in how much sun you're getting, you're going to get a different story, of course. Okay. We find we are able to test. Some of our farmers have been buying these commercial prescriptions. We can see if they're any good. Okay. We can test them and we can say, no, that was bad advice. Or if they're good, we can tell them they're good. And so we wrote a paper on actually a little bit of this. So this is a way for consultants to test their advice. Right. All right. We are going to hold an international conference in Corpus Christi, Texas next January. You're invited, early January, where we are going to have our cyber infrastructure up and running, not in a final form, but in a very workable form. And we're going to offer training, et cetera, and just have a big conference to support this. So this is contingent on us getting some funding, but I'm very optimistic about getting that funding. How can you work with us? You just send me an email. Okay. Better, I should put Bob's email on here. Send Bob an email. Bob's over here not paying attention. He doesn't need to. He knows all this. That's all right. And we'll get you set up. Paul Hegedus is not here, but he's also one of our field trial supervisors, and he's super to work with. So we have some great people who know all kinds of things, and you can work with them. Okay? All right, thank you.